Okay, in this section we want to talk briefly about materials. Materials obviously is a huge subject and there are hundreds of very useful materials, but if I have to say what are the minimal supply of materials a shop or a lab should keep, I will summarize it in what is here on the table and I'll explain what the materials are. So as we said, everything you can make out of cold rolled mild steel sheets should be done that way because it's the strongest, the cheap, maybe not the strongest, but it's strong, it's cheap, it's readily available, you can spot weld it, it works beautifully with bending and water jet. So the general basic material everything should be made of is mild steel, and if you had to only stock two sizes or two thicknesses of sheets, I would stock a gauge 18 and a gauge 10. Gauge 18 is about 1.2 millimeter, gauge 10 is a bit over 3 millimeter, and obviously more gauges are helpful, but if you take a minimalistic approach, with these two gauges you cover 95% of what you will be building. The heavy gauge, the gauge 10, is for making brackets, bases, massive assemblies, and all the rest can be made from gauge 18. Now the same is true for stainless. I would stock a series 300 stainless. As you know, stainless comes in 300 series and 400 series. I would stock a cheapest 300 series stainless. Again, gauge 18 and gauge 12, maybe not 10, because stainless is very expensive. So a sheet of gauge 10 stainless is hundreds of dollars. So this is gauge 18. This is about gauge 12. I would stock these two sizes, and that's all what I need. Now in stainless I would stock two other versions. I would stock some stainless in a spring temper, because it's very convenient to be able to make springs simply by cutting out a sheet which is already spring temper. So this is spring temper stainless. This is type 301 full hard, but you can buy other spring temper stainless. The nice thing about these series 300 in spring temper is that you can still shear them with a shear, you can still bend them if you have to, although they are springy, but they will still take a bend without breaking. For example here, you can still bend it, it doesn't break, but it's still springy. Now you can also buy harder 400 series spring temper stainless, but it cannot be sheared, it cannot be bent, so it's more complicated to use. So as a general purpose spring material, I would store a series 300 stainless, a 301 or some other 300 series in a full hard or three-quarter hard temper. The best place to buy the spring temper stainless is from a company called sidecuts.com, which send you the ends of rolls. When they slit a wide roll, they end up with like 4-inch to 10-inch wide leftovers, and they sell them quite cheap, and that's all that you ever need. Now, and the other type of stainless spring temper I would store is something called a 17-7 stainless steel, and this is a type which is, it comes annealed, it's very, very soft, you can see, it comes annealed, but if you do a heat treating cycle in the oven, it becomes very hard and very springy, much harder, much springier than the spring temper. That's probably the strongest and springiest stainless steel there is. And the heat cycle, you have to follow manufacturer's instructions, but typically you heat it up to 760 degrees, let it cool down completely, and heat it up again to about 580 degrees or some number like that, and let it cool down again. So it's no quenching, just double heating. And then it becomes very, very springy and hard, which means you can do all the forming, bending, spot welding, and everything in the malleable state, and then you take the whole piece, harden it, and becomes very strong and springy. So these are basically the types of stainless I would store. I would also, if you want to stock bars and rods, I would always buy the free machining type, because both steel and stainless come in regular and free machining. Free machining is achieved by adding lead or sulfur or some other alloying element. It costs a little bit more. It's an enormous difference in machining time and surface finish. So since you're not going to need thousands of parts, you just need one, the extra few cents in the material cost will pay back in machining time. So try to stock all the bar stock and plates and everything in free machining. Now, the other metal you should stock some of is aluminum, A for large structures and B in sheets for heat sinks, because copper is better, but copper is expensive. Aluminum is a very good all-purpose material for heat sinks. If I had to stock just one size, I would stock maybe gauge 10 or 12 in an alloy called 5052. Now, the advantage of 5052 is that it can be bent without cracking. The more popular alloy is probably 6061, but if you bend it, it'll crack. Now, I just bend this, and if you zoom here, you can see the crack at the bend. Since a lot of heat sinks have to be bent to increase the surface area, it's better to use 5052. So I wouldn't even bother stocking thin aluminum because, except for heat sinks, I don't see much use for it. Now, another type of material which is good to stock is spring wire. Now, most people, for some reason, don't think of making their own springs, but your springs come in many, many forms, and you always need a spring in a shape that you don't have in your drawer. It's very, very easy to make your own spring, so if you stock maybe just 3-4 sizes of wire, you can instantly make your own springs, both compression and tension. And the way you do that, all that you have to do is you just grip the wire in the chuck together with the mandrel, like this. You can just bend the wire, put it in the chuck, or grip it together with the mandrel. Let's see the direction. Okay? And you just hold it like this. I just started off a bit slow, and then just to grip it. And now, that's it. And now, cut it off. Watch your hands. When you cut off the spring, it will swing around. Okay? Take it out. And now you just have to finish the ends. If it's a tension spring, I will just bend the ends like this. Okay, so basically this thing takes less time than going through your drawers looking for the right spring. Okay, another style of finishing a tension spring is even faster. Another style of finishing a tension spring, you just take one turn, you separate one turn, and you just bend it at 90 degrees, and that's it. So this is a tension spring, okay? If you want to turn it into a compression spring, it's even easier. You just take the tension spring you just made, overstretch it, cut off the ends, and now you got a compression spring. Okay? So now you got a compression spring. Okay? So as you can see, this thing takes seconds. So instead of always looking for the right spring, just have a few coils of spring wire. Again, this wire has two types. One is what's called music wire. Music wire is carbon steel. If you don't need rust proofing or corrosion resistance, it's the cheapest wire. It's available in all sizes. Now, if you need corrosion resistance, you should use the same alloy as this, 17.7. You can buy all the wire sizes in 17.7 stainless. You wind the spring. Now this wire, when it's wire, it only needs one heating cycle, not two, because it's slightly different metallurgically. So it's already pre-treated. So what you do once you made the spring, you put it in the oven according to manufacturer's instructions. Typically it's 480 degrees. This one, the wire goes 480 degrees Celsius for 1 hour. But always follow manufacturer's instructions because of different tempers, and the temper or the annealing determines the heat cycle. Okay, so basically 3 types of stainless plus same alloy in wire, the 17.7, and that's all what you need. Okay. Now, let's talk a little bit about non-metals and other materials. So if I have to choose a minimalistic list of what plastics I will keep. So the first one is something we mentioned many times, polycarbonate or Lexan. It's a very, very good material. It's completely shatterproof, which is quite amazing. You can hit it with a hammer, with a bullet. You can bend it. It takes a fairly high temperature, 100 degrees at least, so it's a very good material all around. Now, another very good all-around material is acetal, known mainly by the trade name Delrin. Okay, so this is white Delrin. It also comes in black. It's a plastic which machines the nicest of all plastics. It's fairly inexpensive, available in all shapes. So it's a good supply of Delrin plate and rod. It's very good. A third plastic, which most people actually are not familiar with, but is very useful, is phenolic laminate. Now this is sold under different trade names, like Garolite or phenolic or whatever. What it is, it's the very original plastic, which is phenolic resin, and layers of cotton fabric laminated together. Now, it has some advantages of a normal plastic. First of all, it doesn't easily deform with heat because it's a composite, basically. It has a lot of fabric. All these plastics, they have a melting point, but they will actually deform much below the melting point in a phenomena called creep. If you put them at, say, 70 degrees C for a long time, they'll creep. Now, this doesn't creep. It doesn't break. It machines very beautifully. And it has it holds threads very well, which those don't. But it has another very interesting property. Because it has the cotton inside with the phenolic, it can absorb oil. So when you make moving parts out of it, they will lubricate themselves very well. So if you lubricate it once, it will absorb some of the oil. So this material is used heavily in gears and bearings. And you can see many things you take apart when you have a steel gear running against a phenolic gear, and this combination lasts forever. It doesn't wear, and it runs quieter than metal against metal gears. For example, this is a small phenolic gear out of an instrument, but you can see these phenolic gears, even large gears. So it's strong enough to make gear teeth, and once you dip it in oil, or once oiled once, it'll keep lubricating itself forever. Okay. So this is phenolic. Now, another material which has good lubricity is Teflon, that you all know well. Teflon also stands a fairly high temperature. It's usable to almost 200 degrees C. It's a weak material. It flows, cold flows. It's weak. It doesn't hold threads. It has very good electrical properties. It's heavily used in RF work if you need some coils, anything to do with high frequency. But it's actually not a very useful plastic because it's too weak. I use it sometimes for bushings which don't have to be highly loaded. That's Teflon. Now, a very cheap plastic is PVC, and another cheap plastic is ABS. And both of them can be also glued together with a solvent-based glue, which is all what plumbers use when you do PVC piping or ABS piping. You can buy the solvent-based glue for it in any hardware store. So you can make big boxes, big structures, which glued joints, which are very strong. So this is a low-temperature material. It's not good for anything, maybe even 70 C or 80 C. It's already pretty weak. But it's very cheap, and it's very readily available, and main thing, available in pipes. So if you need a lot of pipes in any hardware store, you can buy pipes made of that. It doesn't hold threads. You have to put inserts, like I showed in Lexan, helicoil inserts. But it's for just bulky things. If you want to make a big plastic tank, and basically if you can't use metal, if it has to be plastic, you want to make big enclosures, cheap. So these are more expensive materials. This is a very cheap material. Now, there is one plastic which is very expensive but very exotic and good you should stock, and this is polyimide. And polyimide, known as a trade name Vespel. Okay, it's available. Polyimide is available as a tape, which is very useful, and as bulk material like rods or plates. The tape can take up to 300 degrees C, so it's a highest temperature rated polymer there is. So it's very good for electrical insulation. It also has good pierce-through resistance. One of the problems with plastics, if you insulate something electrically and you have some hard corner leaning against it, it'll slowly cut through the insulation. Now this has very good cut-through resistance. That's why it's so good for electrical and temperature. Okay, and it's available as bulk material under the trade name Vespel, made by DuPont, either virgin and then brown shape or filled either with carbon or filled with moly, MOS2, or filled with different materials to make it a better bearing material. So this is an amazing material. It can regularly work at 300 C. Okay, it holds threads very well, it's very rigid, it doesn't distort, it holds shapes very well. It has only one catch: it's terribly expensive. A piece like this could be maybe $100 or something like that. So it's a very, very, very expensive material, but you have to know it exists. So if you need a part which has to be very good mechanically, insulating and high temperature, you don't have much choice. Okay, so this is Vespel. Now, I forgot to mention actually one other useful material to stock a little bit of in metals, and this is bearing bronze. If you have to make anything which slides on steel, the best combination to slide on steel is bronze, not brass, but bronze. It's a huge difference in performance. So you can buy bronze plates, bronze rods, and you just use a little bit of it for a bushing or a wear pad. And if you make parts of this against hardened steel and lubricate it, it'll last forever. Okay, now in terms of other materials, there is Loctite that everybody knows, which is very useful for tight fits, like putting bearings on shafts, Loctiting screws. Be careful about it. This family of materials can cause cracking in plastics. So if you have plastic parts nearby, some plastics will crack, being exposed to vapors or being near that. So you have to be a little bit careful. And one other all-around cheap and useful material is a wax stick. And this is used as for cutting, like if you want to tap or machine aluminum, you just put a bit of wax so the aluminum doesn't stick. Now what this also allows you is to machine aluminum with woodworking tools. So if you have a table saw and you put wax on the blade, you can cut aluminum plates. If you have a router, if you put wax on the blade or wax on the piece you cut, you can route with a normal router aluminum sheets. So it's a very useful material to be a cutting lubricant when you use mainly aluminum, but for other things too. Okay, so let's talk very quickly about steels. The only hardenable steel you need to keep in a shop is a type known as air hardening, or A2. The advantage of air hardening A2 steel over other hardenable steels is double. First, you don't have to quench it, so you just have to heat it and let it cool, and it hardens. And the quenching puts a lot of distortion in the steel. And the second reason is that A2 is optimized to have very, very low dimensional change after hardening. Like if you take a piece of regular steel and you case harden it, or if you take carbon steel and you harden it, you can get significant dimensional change, which means you have to grind away a lot. You have to oversize it before hardening and grind away a lot after hardening. If you make it of A2, you can make it practically net shape. You don't have to machine it after hardening. Maybe you just have to grind a few spots. Now, this is sometimes you have to grind it anyway because the very outer layer of steel decarburizes when you heat it up, so it loses hardness unless you have an inert atmosphere oven. So, as a good compromise, use A2 steel. When you harden it in an oven, you can wrap it in stainless foil to prevent decarburizing. The best thing is you wrap it in paper first and then in stainless foil, and you seal the stainless foil bag, or spot weld it or seal it. So the little air which is inside, the oxygen will be absorbed when the paper carbonizes, and this happens before the steel loses carbon. So if you wrap it in paper, the surface would not decarburize. So Another steel which is useful, especially if dealing with medical devices, is 440, stainless steel 440, which is a hardenable stainless. It's not as corrosion resistant as the 300 series. For example, you cannot leave it in the body as implants, but they use it for surgical tools. And it hardens the same as A2. You just heat it up, let it cool fast, and we'll see it in a minute. Another common steel is high-speed steel, where all your cutting tools, drills, reamers, everything is made of that. Sometimes if you have to do some cutting tool, you can take a piece of high-speed steel and just grind it. You cannot anneal it, you can just grind it. And the other steel is regular carbon steel, which is the cheapest hardenable steel. But as I said, you have to quench it, and there is a lot more knowledge needed, so it's not so recommended. The problem is, if you get them all mixed up, how to tell them apart. They all look the same. The easiest way to tell them apart is by a spark test. You just hold it to a grinder and look at the sparks. So we'll do this here. Okay, so if you take regular mild steel, the sparks look like this. So regular mild steel has very few sparks, and they don't have a star. At the end of the spark, there is no star. If you take carbon steel, same test, there's a lot more sparks, and at the end of the spark, there is a star. Okay, if you take A2, it looks like a different type of spark. It's dimmer and no star. So watch, this is carbon steel, and this is A2. So A2 has darker color sparks, dimmer, and no star. Now, a high-speed steel has even darker sparks, almost no sparks at all, practically no sparks at all, and the few sparks are very dark, like redder rather than white. And the surgical stainless, the 440, again, no sparks at all. So basically, it's hard to tell the high-speed steel from the surgical stainless, but still the high-speed steel sparks just a little bit more. But it's very easy to tell the surgical stainless from the regular A2, because the regular A2 looks like this, and the surgical looks like this. Okay, so let's just talk quickly about hardening. The best way to harden steels is, of course, in a kiln, an oven, but sometimes you have just a little piece to be hardened, and you can do it very quickly with a torch. It's the same way as if you had a little piece to braise. You wouldn't bother to put it in a kiln, you just heat it up with a torch. So the most important thing when you heat things up with a torch is to put some thermal insulator behind the piece you heat up, because this reflects back the heat and prevents the heat from escaping. So basically it's twice as fast to heat something up if you put a piece of fire brick or thermal insulator behind it. Okay? So yeah, here is a piece of A2 steel, and in soft, and I can tell it's soft because I can file it. You can hear just the noise. You can see it cuts nicely. It's a file. So all that I have to do to harden it is get it to white hot and let it cool down in air. And like here it may cool down a bit too slowly because it's insulated, so I just move it away a little bit after hardening. So let me just get tweezers ready. Okay, now the nominal temperature for hardening this is 950 C, which is white hot. It's not so critical if you don't get it exactly right. So you build yourself like a little furnace, maybe even with a cover, so then the heating will be even faster. And if I wanted to braise, it would have been the same. All what you do now is you take the piece of steel and you just put it away, and that's it. Okay, at this stage, after it cooled down, it's fully hard. You can actually hear the file just sliding on it. It's not capable of filing at all. Matter of fact, it's as hard as a file, so you shouldn't do it too much because you're damaging the file. Now, however, at this stage, it is brittle. Brittle meaning, if I will hit it hard with a hammer, it will shatter. So you need to do a second stage called tempering, which is a trade-off between hardness and toughness. So for example, if I didn't do the tempering, I have a little notch here, so it'd probably be quite easy to break because it's completely brittle. See? It had no strength at all. It was very hard, but I could break it easily. So in order to temper it, you heat it to anywhere between 250 C to 300 C, depending on the trade-off you want. 250 C will keep it at hardness of Rockwell RC60, which is basically as hard as you need for almost any application. If you need it something to have impact strength, then you have to heat it a bit more to 300 C. Then you go down to Rockwell 56 C or something like that, but you have much better toughness. So that's the range basically, 220 to 300, and every 10 degrees makes a big difference. So you have to be able to judge the temperature. Of course, you can do it in an oven accurately, but if you want to do it quick and dirty with a torch, like we did it here, you will judge the temperature by the color. Luckily, steel has a very nice color change in this range that we need. It goes from straw color, say at around 220, it goes through brown, through very dark blue, to light blue, which is about 300 C. So first I'll show you the color change, just so you get an idea. So this is straw color. If I check it, here it says 196. It probably was a bit more because it cools down very quickly. Okay, so here it says 200, and that's just a straw color. If I go a bit darker, like dark blue, this is dark blue, it says 240. It's actually a bit more again because as soon as I move the torch away, the temperature drops. This dark blue is actually 270, and if I keep heating it to light blue, it says 330, but that's already overheated. So if I look at this piece and I look at the color gradation, I can see straw, dark blue, light blue, and this was overheated already. It went gray, so that's overheated. So the tempering range is straw to dark blue. So dark blue is Rockwell, say 56, 55, Rockwell C. Straw is Rockwell C 60. Okay, so say we'll want to temper this piece for full hardness, so we'll temper it to straw color. Small flame in order not to overheat, it's very, very critical. Okay, very small flame and just keep moving, so in order not to overheat one spot. And that's it. Remember, if the part had an asymmetric shape, so if the part looked like this, and this was thin and this was thick, I would direct most of the heat of the torch to the thick part, because otherwise this will overheat. So I just very carefully watch how much mass I have and play with the torch longer on the heavier sections. Okay, so this is now light straw, so it's full hardness. We can verify that. You can run a file on it. Actually, you can hear by the sound that the file doesn't even bite into it. Don't overdo it because you damage the file. It's as hard as a file. One useful thing here is sometimes if you want to make some cutting tool, like a homemade drill or homemade cutting tool, is you can braze a piece of carbide from some discarded carbide insert to a stem of mild steel, And you do it just like the brazing you've seen before with a setup like that. You put a piece of carbide on it, a bit of flux, a piece of brazing alloy, heat the whole thing up, and then you have a carbide tip, which is quite useful. It's very useful if you make yourself special drills, special size drills. Shape cross-section. If you heat up the glass So now what we'll do is and see that it maintains its D-shaped perfectly. very esoteric use, but if you need this kind of prismatic shapes, squares, triangles, aspheric lenses, it's